Hi, I'm Hannes, and together with my co-first author, Octavian, I'm going to introduce EquiBind, where we predict the 3D structure in which a small molecule binds to a protein.
Hi, I'm Octavian, and let's dive into the details of our EquiBind models. We take as input a ligand graph, which we convert to an initial random RD-kit conformer, and also a protein structure, which is going to remain rigid. Our EquiBind model is going to predict where the drug attaches to the protein, in what orientation, and also the internal conformational change. We do that by taking the two molecular structures as input and predicting two key point sets of equal cardinality. After that, we can superimpose Y1 and Y2 with differentiable capture algorithm to recover a rigid transformation to bind the ligand into the receptor. Importantly, we take this idea of single object group equivariance, which was developed initially for convolutional neural networks, and now we generalize this for multi-objects to incorporate independent SS3 transformations. So our EquiBind model is going to take the two molecules as input and predict two key point sets as output. If these two molecules are transformed with independent SS3 transformations, then the output of our EquiBind model, if it reverts these independent SS3 transformations, is going to close this diagram. The way our architecture works is that it first converts the two individual molecular structures into k-nearest neighbor individual spatial graphs, and then applies previously developed independent SS3 equivalent graph matching networks, which consist of intra and interneural messages. We stack several such layers to jointly transform coordinates and features of the two molecules. A core property of this architecture is, by design, guaranteeing independent SS3 equivariance of coordinate embeddings and invariance of feature embeddings. Finally, we project these transformed coordinates and features into two ligand key point sets and receptor key point sets of equal cardinality using multi-head SS3 equivalent attention. This is going to give us an SS3 docking transformation, and additionally takes the transformed coordinates of the ligand and trains them with an additional loss to represent the bound coordinates of the ligand. And in order to obtain biologically plausible deformations of the ligand, we are going to change only torsion angles of rotatable bonds of the initial conformer to fit the transformed coordinates by maximizing a von Mises log likelihood in closed form as a post-processing step.
Now let's test EquiBind. The dataset that we'll use is PDB-bind, where we have 19,000 complexes of proteins with the small ligand bound to them, the 3D structures of those. And for testing, we use all complexes that were released in 2020 or later. And for training, we use the older ones, but we also make sure that we have no shared ligands. We compare EquiBind against methods that sample many 3D positions and then score them. And there we have 3 physics-based scoring functions, and also GNINA, which is a deep learning-based score function. Let's first have a look at this section of the table over here. There we show the number of seconds that it takes on average for a method to make the prediction for a single complex. And we see the time for the baselines here. If we additionally look at the EquiBind number, then we can see we really are magnitudes faster. Now let's have a look at these curves over here, where on the x-axis we have the error of our predictions, and on the y-axis we have the fraction of predictions that is better than this error. So the optimal curve would look something like this, right? And we can see that EquiBind in orange here, in this upper region, it is doing better than the baselines. But in this very low angstrom area, there we're actually doing worse than the baselines. So because we know that EquiBind is good at getting the approximate location right, we first use EquiBind to get a prediction, then we fine-tune it with SMINA. And that's how we end up with this light blue curve over here and can get the best of both worlds by trading off runtime with quality. Here we are looking at an important target protein, and in green we have the configurations in which 2 drugs bind to it. These we would like to predict. Then we can look at the predictions of some baselines. With GNINA, we predict both drugs to be in the same pocket, so one of the predictions is wrong. Similar with SMINA, we predict both to be in the other pocket. And Glide switches both of them around. Meanwhile, the predictions that we get with EquiBind, there we see EquiBind is able to get the right approximate location, and then with SMINA we fine-tune and almost get the perfect final configurations. Finally, I want to invite you to head over to GitHub to check out our code there, use it to make your own predictions, which is really easy to set up. And also, we're always very happy to hear from you, so feel free to reach out to us.